Mr. Tarrou, in this trig lesson, we are going to be going through a couple of examples where we look at the picture of what looks like maybe a sine or cosine wave and come up with an equation that would represent that graph. Now, these are cyclical functions, and what that means is that you can come up with an infinite number of answers, an infinite number of equations that would graph out to match, the given graph. So your teacher, your textbook, is going to have to give you some limitations. Maybe they'll say that your amplitude needs to be positive or negative. You're only allowed to come up with a function in terms of sine or cosine. Make sure that your phase shift is the smallest positive value possible, because every person in the class could really give a different answer and yet still be correct. Now, what that means is, as we go through our couple of examples, I'm actually going to come up with a few, together we're going to come up with a few equations to match the first graph I give you, and then we'll just finish up with one more and give one possible answer for that picture. Okay, so first we have to understand how to graph sine and cosine before we try and come up with equations, of course, from a graph, and hopefully we've already studied that. I'll put a link in my description if you want to review how to graph trig functions without a calculator. And just a quick rundown, I have two forms here of sort of like the general form of these trig equations with all the transformations included. This first form would match how my pre-calculus book introduces this, and the second line would match how an old trig book, and actually current trig books as well, but years ago I taught out of a trig book for my school, and this is how it wrote the general form of trig functions. Showing you all the different transformations. And really I like the second form better, but you need to, of course, realize that different textbooks use different notation. So the amplitude, of our sine and cosine functions is equal to the absolute value of A. If you're looking at your equation, of course, at least I hope it is, you realize this, and your leading coefficient is negative. That means you have a reflection over the x-axis. At least, well, you do have that reflection before you apply the vertical transformation. And then we've got a sine of bx minus c, or a sine, and I'm just writing sine just to have something trig function to write. This would be sine, cosine, tangent, cotangent, whatever. Your trig function here. B times parentheses x minus c over b. Now, when you have factored out if there is a leading coefficient of that inside independent variable, normally x, if that has been factored out in your your coefficient is 1, this is the leading coefficient out here, a. If that coefficient on the x is 1, then you can look inside that parentheses next to the plus or minus and see the phase shift. Now, because my pre-calculus book writes the general form like this, I need to off to the side say that the phase shift is equal to c over b. If you're using a book that just automatically has the b out front and this coefficient on the x equal to 1, you might just see a c here and it says the phase shift is equal to c. So again, just be consistent with your textbook. And then we have an addition of a constant outside of the actual math function, not inside the math function, but outside, and that is your vertical shift. The absolute value of A is the amplitude of your sine or cosine function, and it is equal to half of the overall height. The period, at least for sine, cosine, secant, and cosecant, is calculated by doing 2 pi over b, that coefficient of x, or that coefficient that has been factored out and put in front of those parentheses. If you're talking about a tangent or cotangent graph, this would be pi over b. Either c over b, or if your textbook has this factored out again and this coefficient of 1, whatever comes after that minus in your general form will be the phase shift. For my pre-calculus book using this notation, c over b is going to be the phase shift. And if you see c minus c over b, that's a phase shift to the right, c over b units. And if you have an x plus c over b, that really means that that c over b value is negative. To have created that plus sign, see the minus sign is already in the standard form, or general form, whatever your book calls it. That phase shift would have been negative to cause that negative right there, that minus, to change to addition. Okay, so x minus c over b, really the phase shift is positive c over b. You have a phase shift to the right. x plus c over b, that really means your phase shift is negative c over b, and that is meaning that your graph has been shifted to the left that many units. And then finally d is equal to your vertical shift. And when looking at the picture, the graph, that is going to be the average of the max and min. The vertical shift, like when you look at a sine and cosine wave, and this is another example of why there can be so many different, basically almost an infinite number of equations you can come up with to represent a particular graph, and why you need restrictions when given these problems. We have in green the cosine graph, and in orange we have the sine graph. Well, look at them. Sine is y over r, cosine is x over r, so sine and cosine both have that same denominator of r, and the only difference is, for one the numerator is x, and for one the numerator is y. Well, those x and y values are coming from a unit circle that has the origin as its center. So when you look at that y over r and x over r ratio, ultimately you're really getting the exact same shape. It's just that they're shifted a little bit, and that phase shift is, well, let's see. It looks like by my picture that if I moved this to the right, what color have I not used yet? If I take the cosine graph and I shift it to the right pi over 2 units, it would line up exactly on top of the sine function. And they are. The sine curve and the cosine curve are exactly the same shape. Let's see here. Thinking about unit circle, the cosine of 0 is equal to 1, and the cosine and the sine of, let's see here. Let's say, how am I going to say? I know what I want to say, but the cosine of 0 is 1, and the cosine of pi over 2 is 0, whereas the sine of 0 is 0, and the sine of pi over 2 is equal to 1. You're getting those same values just at pi over 2 radians apart, or 90 degrees if you're working with degrees. And so sine and cosine, the curves are exactly the same shape. So when I look at a sine wave or / cosine wave, I could come up with an equation using the sine function, and I could come up with an equation using the cosine function. The cosine function starts, if you will, really these graphs go on left and, they go left, right forever. Their domain is all real numbers, but if you think of where the y-axis is, where x is equal to 0 is the quote-unquote starting point, the cosine, the parent function for cosine, starts at its maximum value, 1. Cosine of 0 is 1, cosine of pi over 2 is 0, cosine of pi is negative 1, and yeah, you start off with its maximum value of 0, 1, and then it just starts to cycle from there, and obviously goes back to 1 at some point. And the sine function starts sort of like in the middle of its cycle, not at its minimum, not at its max, but in the middle of its cycle, if you will, the vertical cycle that we have, and it starts at 0, 0. So just looking at our parent functions here, write a cosine function whose graph lines up with the sine. In other words, I want to write an equation that would line right on top of that orange sine function, but have it in terms of sine. Well, that's what I was just trying to talk to you for the last 5 minutes. There's a phase shift of pi over 2. So if I could take this cosine graph, push it to the right, and then, I could move it to the left as well at some point, right? It's going to line up over here. But if I push it to the right, pi over 2 units, it's going to line right up. So we have y is equal to the cosine of x minus pi over 2. And if you want to see that on a graphing calculator, I'll just show you right now. So we're going to go toggle to the graphing window of our TI Nspire calculator. And we've already got the window open here. And we're going to type in y is equal to the sine of x and enter. All right, so here we got that one going. We're going to hit the tab button again. And these are all, by the way, these graphs are in radians. Now we're going to type in the cosine. There we go. Cosine of x, and that, of course, is going to look very similar, but with that phase shift that we were discussing. And now what we're going to do is type in the cosine. So again, tab, open up that entry window, and this time I'll show you with the cursor here. Cosine, oh, well, we don't need to type it in that way. We can just go to trig, cosine, put in x minus, hit the control division button and set up a fraction. We're going to put in pi over 2. And that should line up right over this new graph. It should be in a different color, line right on top of that cosine, or that, that sine graph. And there you go. So we had that blue line, and now it has been turned black because we have put over it the black line created by the equation y is equal to cosine of x minus pi over 2. And let's get back to our lesson. Okay, so that's what it looks like on a calculator. You saw the two graphs line up exactly on top of each other. Let's get to something a bit more, a graph that has a lot of transformations to it. It's been moved left and right, up and down, all kinds of good stuff. We've changed the period, and see if we can't come up with an equation that would represent that graph. No. Alrighty then. Write an equation for the given graph. And there's no restrictions. I didn't tell you that the amplitude had to be positive or the phase shift had to be positive or negative. I didn't say use sine or cosine. So we're going to come up with many examples for this particular graph. Now, well, I can see right off the bat, it doesn't seem to be, centered on the x-axis anymore. It seems to be a push down, so there appears to have been a vertical shift. And maybe this isn't the most, complicated example. Plus, you can kind of see the dots that I've put on the graph to help me plot or draw the picture. But assuming we didn't see that, let's go through the calculations we need to do to figure out what the 4 transformations were. So first of all, what's the period of this sine/cosine graph? Well, the period of sine, cosine, secant, and cosecant is the phone. Okay, well, we got that phone. Let's get back to the period, which is equal to, for sine, cosine, secant, and cosecant, is 2 pi over b. If it was tangent and cotangent, that would just be pi. So our period, well, let's see. There's a few places we can look at in this pattern to try and identify it, but the minimum values or the maximum values would probably be the easiest place to look, and we have a minimum value at x is equal to 0 and another minimum value at x is equal to pi. So that's pretty simple. Our period is simply pi. So what does b need to be to, figure out what that is? And yeah, I know 2 divided by 2 is 1. But in case it's something that maybe we can't just look at, we're going to multiply both sides of this equation by b and get 2 pi is equal to b times pi. Divide both sides by pi. And of course, b is equal to 2. So we'll be using that to write, of course, our equation. The amplitude is equal to half of the overall height. So we're going to find that overall height. I guess I could get, fancy and use some absolute value functions and just say, do some kind of subtraction with the max and mins. But if you put the max first, you're always going to get a positive answer. So the amplitude is going to be 1/2 of the overall height. Well, we have a maximum value, y value of 1. We have a minimum y value of -3, and 1/2 of 1 plus 3, which is 4, is equal to 2. So now we have a value for a. All right, so we have the period, we have the amplitude. Let's talk about phase shift. Well, the phase shift, what you come up with that is going to depend on whether you want to write an equation in terms of sine or cosine. And I want to do both, but let's just, for argument's sake, let's do a phase shift for setting up an equation that is in terms of the cosine function. Well, the cosine function, as I just had on the board a second ago, the cosine of 0 is equal to 1, and then, when I talk about graphing trig functions without a graphing calculator, I always talk about graphing the quarters. Find the period and divide by 4, and that's your easy points, because around the unit circle there is, well, 1, 2, 3, 4 easy angles that are going to give you values of either 0 or 1 from the trig function. And then you have other things going on in in the equation, it may be ultimately your final answer is not, 1, 0, -1, but that's what you get from the trig function, so they're easy. So looking here, remembering the period is equal to pi, and the easy points are found at the values which are 1/4 of the period. Well, 1/4 of pi is equal to 1/4, and so the cosine graph, the cosine of 0 is 1. The cosine at the first quarter, the cosine of pi over 2, if you will, but this has a period change, is equal to 0. And then it goes through, halfway through its cycle, your cosine at halfway through the cycle, normally it's pi, right? If you haven't messed with the period, is -1. And then it cycles back to 0 and goes to +1. So that would be this dotted line. I'm trying not to dominate the graph with, but that little blue dotted line would be what the cosine function would look like if all you did was change the period from 2 pi to 1 pi. Now, the cosine graph starts at a maximum value. Well, this function is starting at a minimum value. So if I take that graph and I just reflect it over the y-axis, or excuse me, the x-axis, then I can kind of get away with not having a phase shift at all. So the phase shift for cosine, and we taught, this is a cyclical graph, so we can move it horizontally all kinds of ways. I can see here that I can take my blue line, and if I shift it to the right pi over 2 units, I can have that maximum match up with that maximum. So the answer we're about to come up with is not the only answer, but let's go ahead and let the phase shift equal 0. So C over B, or whatever notation your textbook is using, at least for this first example, we're going to let it equal 0. Now, and we're going to achieve that again, making this line up by doing a reflection over the x-axis. Now there's also a vertical shift, and I can see that, again, with my points, that it's been moved down 1, but in case you can't just see it with a particular graph that you're working with, the vertical shift well, that is the average of the maximum values. So we're going to, for the vertical shift, we're going to take the maximum value of 1, we're going to add it with the minimum value of -3, and we're going to find the average of that. Well, 1 minus 3 is -2, and -2 over 2 is equal to -1. So D, our vertical shift, is -1, and if you can see it from the graph, just write it down. But if you can't, that is how you're going to calculate the vertical shift. So I have all 4 transformations kind of figured out for at least one possible answer, and that means that we're going to be able to represent, if we were to graph y is equal to, let's see here, the amplitude was 2, but if I take this standard, well, almost standard cosine function and stretch it out 2, it's going to start at the max value, not the minimum value, so we're going to make that -2 cosine of, now I'm going to use that notation, that standard notation that had the coefficient of x set to be 1. So it's going to be b, which was 2, times x minus, and this way I can just, once I identify the phase shift, I can just write it in the equation if I have that b factored out. But at least with our first possible solution, it is a solution, but one of many that we could possibly come up with, our phase shift is 0. And you don't really need to write that, but just for practice sakes. And our vertical shift was -1. Okay, now another version of this. Let's see here. Yeah, I just want to, I don't know why I'm looking at my notes. There's all kinds of different answers, but just to stay consistent with that, what if the directions in your book said that you had to have a positive a? So this is one possible answer, but my a coefficient is negative. Well, what if the direction said a must be positive? And I kind of just verbally already gave away that answer, but y is equal to 2 cosine of 2 minus 1, and now I just need to work with the phase shift, because if I'm not allowed to reflect the graph over the x-axis, then I can't start with a minimum value. I'm still going to quote-unquote sort of start with that maximum value. So again, looking at this this light dot blue line standard representing that standard almost parent function for cosine, I need to push that maximum value to the right, pi over 2 units. So now that would be, again, 2 cosine time, of 2 times x minus pi over 2, close up the parentheses and subtract 1. And that is another equation that when graphed would line right on top of that yellow function, or the given yellow graph. Now, what if so I guess for that orange this is not correct, right? So pay attention to the color coding. What would my phase shift be if, and so let's do another color here, we haven't used green yet. What would the phase shift be, even though we've already come up with 2 versions, if we wanted to do or work with the sine function? Well, the sine function, I'm really kind of afraid the green's not going to stand out enough against the blue dotted one, but that's the most different color I have. I've already used red and orange. So kind of play with me here. A sine function with a period of pi, so the sine function would start at 0, 0, rise to its, let's just do this solid, rise to its maximum value of 1, 1/4 away through its period, and then the sine of pi, or halfway through its period, would be back to 0, and then -1, and then back to pi. So this was what the sine function would look like if all you did was change the period to pi. Now, with the sine function, there's a few things you can focus on. I think you could think of the 0, 0, and this is, I've tried to draw this pretty neatly. We've moved to the right pi over 4 to get that center point to match up with the sort of center point of the given graph. See, halfway through the max and min is that center line of the graph, which used to be the x-axis before it had a vertical shift applied to it. You could also look at the maximum values. We have a maximum pi over 4, and this maximum is at pi over 2. So however you look at it, pi over 2 minus pi over 4 is going to come out to be pi over 4. Or this is at 0, 0, and this point in the center of the cycle here is at pi over 4, -1. So hopefully at some point there I've made sense, had it make sense for you. The value of c over b is going to be equal to pi over 4. And so now we've got, at least in terms of sine, y is equal to, we're starting in the center going to a maximum, we're starting at the center going to a maximum, so there's no reason with this particular phase shift to have to do any kind of reflection over the x-axis. We have y is equal to 2 sine of 2 times x minus pi over 4, because again we're shifting this to the right to make it make sort of the almost parent function line up with the given graph in the problem, -1. And there's 3 answers, all that match this yellow graph. So I'm going to again show you that on the graphing calculator, and we'll come back and we'll do our last example. Well, right now, I guess. No. So here we are again with our TI Nspire. We're going to hit this button over here to the left of the touchpad to toggle to our graph, which will nicely already be open for us. Our first answer to match the given graph was y is equal to -2 cosine of 2x, get out of those parentheses, -1. And then we're going to hit enter. That looks pretty good. We're then going to go ahead and hit the tab window, open up the next entry. The next version of this next equation that we came up with to model that given graph was 2 cosine of 2, open up another set of parentheses to get it exactly in the format I wrote on the board, x minus, control divide, get that fraction window opened up there, pi over 2. minus 1. And that should line right on top of our previous graph. And there we go. Seeing it line right on top. We don't even see that blue graph anymore. And our final version, tab, 2 sine of 2 parentheses, whoops, x minus pi over 4 is going to be then subtracted by 1, and voila, let's hope. Yes, now we have our third graph lining right on top of the previous two, and I'll just grab this equation and move it somewhere else in the window. And there we go. We got a red, blue, and black graph all lining right on top of each other. Last example. Write an equation in the form of y is equal to a cosine of b times x minus c over b plus d for the given graph. Now the only restriction I'm giving us is cosine. I'd really need to give us quite a few restrictions again. Amplitude positive, make sure your phase shift is the, I don't know, whatever smallest absolute value possible or something like that. We're just going to come up with one equation and be done with our lesson. So, well, let's see here. Like before, we need to find the value for a, b, c or c over b, whatever your book is using, and then d, the vertical shift. So the amplitude. Well, the amplitude again is 1/2 of the overall height. So the amplitude, it's a little bit sloppy, is 1/2. The maximum value is 8. The minimum value is 2. So it's 1/2 of 8 minus 2. That is the sort of total height, if you will, the vertical distance between max and min. And half of that, well, 8 minus 2 is 6, and half of 6 is equal to 3. What is the period? Well, the period, excuse me, is 2 pi over b. And, okay, let's see here. How far is it between, the 2 points in the middle of the cycle, or the 2 maximum values, which I think are really kind of easier. So I've got my x-axis marked off, and here we've got a maximum value at what looks like negative 1/4. So let's go from large to small. So this is coming down here at somewhere between 3 over 2 and 2, but these tick marks are like in the middle, so that's 1/4, 2/4, 3/4, 4/4, 5/4, 6 over 4, 7 over 4. So we're looking at 7 over 4 minus this x-coordinate, which is negative 1/4. If I wasn't purposely setting up large minus small, I'd have to wrap this in parentheses to make sure our period or length is a positive number. That's going to be 8 over 4, which of course is equal to 2. So looking at this equation now and trying to solve for b, we're going to multiply both sides by b, and we're going to get, I guess I can just maybe put it here, 2 pi is equal to 2b. We're going to divide both sides by 2 and get that pi is equal to our coefficient of b. So now we have a value of b, we have a value for a, and we have, okay, so we have something for setting the amplitude, something for setting the period. We need to figure out what the vertical shift is going to be. So the vertical shift, let me just write, I'll write it out. Vertical shift, often I just put VS for vertical shift, is the average of the max and min values. So that's going to be, the maximum value is 8, the minimum value is 2. We're adding these because we want to find the average, not a sort of distance, if you will. So 8 plus 2 is equal to 10. Divide that by 2, and we get a vertical shift of 5. And again, I'm kind of leaving my points up here that I've used to graph the function, and that center line is 5 units above the x-axis. Our phase shift, now here's where we can come up with all different kinds of versions, equations that represent, or will graph out to line right over that top of that graph. Our phase shift just wanting to keep this phase shift as small a value as possible. And also we're wanting to have an equation in terms of cosine. So our period is equal to 2, and you don't necessarily really need to do this. I do think it helps visualize though. A cosine graph, the cosine graph starts at its maximum value. Our period is 2, so it's almost like this would be, well, I can't see through my hand. So that dotted line would be kind of like where the cosine graph would be if all we did was change the period from 2 pi to a period of 2. Now that maximum point is at 0, 1. Now this maximum point, I know it's way up here at 8, but we've already talked about vertical shifts and the amplitude change. That maximum point is happening at an x-coordinate of negative pi over, oh, excuse me. I know, we always think about that x-axis having pi's in it. That maximum value is at an x-coordinate of negative 1/4. Well, there's also a maximum value over here at, what was that? 7 pi over 4. So we could, do a shift to the right as well, but keeping the phase shift, like I said, as small as possible, whether it's positive or negative. If we take this cosine graph and shift it to the left 1/4 of a unit, then our maximum, instead of being at 0, our maximum will be at negative 1/4. So, get that negative in there. So our phase shift is going to be, well, our C over B or C or whatever your textbook is using to identify the variable of phase shift is going to be equal to negative 1/4. And that's what, so we have all 4 things now that we need to write the equation, at least one version of an equation that lines over on top of, or graphs right on top of that, well, given graph. Always seems weird to say graph twice in the same sentence. So y is equal to, we're starting at the maximum, and we're kind of basically going to be starting at a maximum, so no need for the any kind of reflection over the x-axis, at least not with this version of our answer. So 3 cosine, our period was 2, but to get that period of 2 from the standard 2 pi over b, that means that b needs to be equal to pi. So we have cosine of pi, parentheses, again keeping that coefficient of the x equal to 1, so we can just plug in the phase shift value, which is negative 1/4. So x minus a negative 1/4, close it up, and our vertical shift is equal to 5. So our final answer is y is equal to 3 cosine of pi times x plus 1/4 plus 5. And that's not the only answer, but it's the one that we've come up with, and it does match the given graph. So I am done. I'm Mr. True. Bam! Go do your homework.